The Hubble Space Telescope witnessed something it should never have seen: a small interstellar visitor, known as 3I Atlas, spinning faster, with no source of added energy. This is the paradox: a rotation that accelerates in the silence of space, a motion that defies every law we use to describe momentum, a violation with no torque, no thrust, no impact, no reason. In the vacuum between stars, nothing pushes, nothing pulls, nothing whispers a force into an object this small. Yet the data from the Hubble Space Telescope shows a drift, a rise, a measurable increase in spin rate, as if 3I Atlas were tapping into an unseen reservoir, stealing motion from a place we cannot detect. The darkness around it remains still, cold, unmoved. The object alone changes. This is how the anomaly begins. Not with noise, not with a flare, but with silent acceleration. A signature that should be impossible. A rotation that should be fixed forever. Scientists checked for jets. They checked for debris. They checked for hidden fragments shedding into space. Nothing appeared. The measurements held steady. The anomaly refused to fade. Momentum cannot grow without a cause. Angular velocity cannot rise in a vacuum. Every equation demands a source. And yet, 3I Atlas keeps spinning in the calm isolation between stars, where the laws of motion should be absolute. Something is slipping. Something is bending the rules we trust. And the question waiting in the dark is simple. If this object can gain rotation without energy, what else can the universe do when no one is watching? 3I Atlas did not arrive with a warning. It did not blaze across the sky. It slipped into our instruments quietly, barely brighter than the background noise of the cosmos. Its discovery began with a routine survey, a sweep of faint objects moving against the stars. Astronomers first flagged it as unusual because of its speed. Not extraordinary, but wrong for anything born inside our solar system. Its trajectory pointed from deep interstellar space, a path untouched by the gravity of our planets, a path that carried the cold signature of a visitor. The detection was confirmed through multiple observations. Wide-field telescopes narrowed its position. Minor variations were tracked. And then, the moment that changed everything. The Hubble Space Telescope locked onto it. Hubble gathered detailed photometric readings. It resolved a pattern, a pulse in brightness, a rhythm that did not match noise, a rotation. At first, it seemed ordinary. Many small bodies spin as they travel. But when researchers compared early measurements to later ones, the numbers did not line up. Something was increasing. Something was accelerating. The spin rate had changed. 3I Atlas was rotating faster than it had when first detected. Not by much, but enough to violate every prediction. Enough to break the conservation of angular momentum. Enough to raise eyebrows inside institutions that do not raise eyebrows easily. The early study group began a torque investigation. A simple question guided them. What force could be acting on it? They checked for sunlight-driven acceleration. They searched for thermal lag effects. They examined possibilities of asymmetric outgassing. Every pathway led to the same dead end. There was no torque. The object traveled through near-perfect vacuum. No gas, no dust. No solar wind variations strong enough to matter. Nothing that could whisper even a fraction of the energy required. And yet, its spin kept rising. Historical comparison made the anomaly worse. Data from its earliest detection showed a lower rate. Data from later Hubble sessions revealed the uptick. Confirmed, verified, repeated. 3I Atlas was not just rotating. It was changing. Its origin remained silent. Its surface showed no active jets. Its path revealed no interactions. It behaved like a quiet stone drifting through infinite darkness. Except for the one thing it should never do: accelerate. This is why the discovery matters. Because an interstellar object brings with it a piece of another world, another system, another history. And if that piece refuses to obey our laws, then the mystery is no longer about where it came from, but about what it is becoming. To understand the anomaly of 3I Atlas, we begin with the simplest principle in rotational physics. An object in space should spin at a constant rate, unless acted upon by an external torque. This rule is foundational. It is universal. It is supposed to be unbreakable. Yet 3I Atlas bends that rule in silence. Imagine a lone fragment of matter drifting through interstellar darkness. No atmosphere, no drag, no friction. Its rotation should be preserved forever, a perfect time capsule of its last collision or formation event. But the measurements say otherwise. The light curve of 3I Atlas tells a different story. Hubble recorded a periodic dimming and brightening, a clean rotational signal. And over time, the period changed. Shorter, faster, tighter. To detect this, scientists relied on photometric phase shifts, minute alterations in how sunlight scattered across the object's uneven surface. Each pulse of reflected light carried a timestamp. Each timestamp fed into a rotational model, and the model refused to stabilize. The anomaly grew sharper with every pass. Researchers split the signal to rule out noise. They compared multiple observation windows, and what emerged was unmistakable: a gradual acceleration in rotation, as if the object were experiencing a soft push, a push no one could identify. In a vacuum this clean, any detectable torque must come from one of three sources: outgassing, tidal interaction, or radiation pressure. Outgassing would leave a visible plume. 3I Atlas showed none. Tidal interactions require a nearby massive body. There was nothing in range. Radiation pressure from the sun can twist objects, but the effect is tiny, and this acceleration was not tiny. The anomaly refused to fit the known categories. Some researchers explored deeper possibilities. Could the surface be unevenly absorbing heat, re-radiating it in patterns that mimic thrust? Thermal modeling dismissed that quickly. The required temperature asymmetry was physically unreasonable for an object this size. Others asked whether it could be shedding microscopic mass, but that would cause observable motion changes, a drift in trajectory. 3I Atlas moved steadily and cleanly. No thrust, no shedding, no energy input. Imagery from Hubble suggested a rough and possibly fractured geometry. Angular faces, jagged shadows, an irregular shape that should stabilize into a steady rotation. Instead, that shape seemed to amplify the mystery. Then came the torque violation study. Scientists examined formal uncertainties in the rotational model. Covariance drift across multiple observations. Inertial frame comparisons using star field anchors. The anomaly persisted. Uncorrelated with instrument error. Unrelated to background fluctuations. Whatever was happening to 3I Atlas was real. Picture it now. A dark shard carving through the solar system. Sunlight striking it at a shallow angle. Its rotation subtly rising, as if responding to a silent command. This is where the science tightens. Because every known natural process that increases spin leaves a signature, a chemical trace, a thermal pattern, a trajectory shift. 3I Atlas leaves nothing. Its acceleration is clean, narrow, silent, like a whisper made of motion. And the deeper scientists look, the stranger the question becomes. Not how it spins, but why it refuses to stop changing. This is the part of the story where the facts grow darker. Not because they point to anything supernatural, but because they point to something we cannot yet categorize. 3I Atlas carries a list of strange measurements, each one subtle, each one quiet, each one pushing the object further outside the boundaries of normal physics. The first strange fact is its rotational curve. Most accelerating objects show a pattern, a taper, a plateau, a hint of decay. 3I Atlas shows none. Its acceleration is steady, linear, almost disciplined, as if the force behind it knows exactly how much energy to give and exactly when to give it. The second strangeness lies in its light scatter. Hubble detected micro fluctuations in brightness that do not match surface roughness alone. Tiny spikes, sharp dips, moments where the reflection pattern trembles. For a natural object, this is rare. For an interstellar fragment, it is nearly unheard of. Some analysts suggested a tumbling motion, a chaotic rotation common in irregular bodies. But the data does not fit. 3I Atlas does not tumble. Its rotation is smooth, predictable, laser steady. A level of stability that contradicts the small fluctuations in its brightness. A contradiction inside a contradiction. Then there is the torque violation study, a detailed examination of angular momentum drift over multiple observational windows. Researchers found a pattern of acceleration that was too clean, too coherent. Formal uncertainties tightened instead of widening. Covariance drift across sessions, a statistical signature that should be impossible in a system with no external forces. The deeper they looked, the less sense it made. Another anomaly followed, its color index. 3I Atlas reflects light in a spectrum that does not conform to typical carbonaceous interstellar debris. It is not metallic, but it is not purely rocky either. Its readings fall into a narrow valley between known categories, as if it were made of something we rarely encounter. Something shaped by conditions our solar system never produced. Then came the mass inconsistency, a subtle mismatch between rotational behavior and estimated density. If it were denser, its acceleration would be harder. If it were lighter, its shape would deform under its own spin. But it does neither. It behaves like a compact object with a hollow signature. Dense enough to hold form, light enough to accelerate. A paradox of structure. These details are not dramatic. They do not shout. They whisper. They whisper of an object shaped far from our sun, in conditions we do not yet understand, under forces we cannot fully map. A quiet shard from another system, carrying quiet rules from another star. And then there is the final strange fact, the one that worries researchers the most. As 3I Atlas accelerates, its internal stresses should rise. Its fractures should grow. Its body should weaken. But it shows no signs of disruption. None. It spins faster and faster. And yet its structure holds. A normal object would tear itself apart. This one does not. The silence around it deepens. The vacuum remains unchanged. But the object refuses to behave like something merely drifting. It behaves like something responding. To what? No one knows. And this is where the darkness settles. Not in fear, not in speculation, but in the quiet admission shared across observatories. We're watching a natural object break natural rules, and it is doing so with perfect calm. The future of 3I Atlas is not measured in mystery alone. It is measured in what its anomaly forces us to confront. Because when an object from another star system breaks the rules of rotation, it breaks more than equations. It breaks our assumptions about how quiet the universe truly is. The first implication is scientific. A rotating body that accelerates without torque challenges the conservation laws that anchor modern physics. If even one interstellar object can drift outside those laws, then the boundary between what is fixed and what is flexible becomes thinner. Researchers will have to refine rotational models, rewrite assumptions about small body dynamics, and question whether interstellar fragments can carry physical behaviors shaped by forces we have never encountered. The second implication lies in technology. Objects like 3I Atlas can teach us how matter survives the stresses of deep space, how it preserves structural integrity under rising spin. If its resilience comes from a unique composition, we may learn new forms of material science. If its acceleration comes from internal processes we do not yet understand, humanity may uncover new pathways of energy transfer or rotational control. The third implication is observational. 3I Atlas proves that our instruments must become sharper, more patient, more unforgiving. If a small visitor can hide its anomaly inside subtle light curves, then larger mysteries may be slipping past us. Objects that refuse to follow expected patterns. Objects that teach us new physics, quietly, without spectacle, without warning. The fourth implication is cosmic. Because if 3I Atlas carries the silent fingerprint of another system, another star, another formation history, then its behavior may reflect conditions far beyond our experience. Extreme thermal gradients, exotic chemical layering, rotational fields shaped in environments our sun cannot reproduce. Every anomaly it carries may be a message from a place we have never seen. And finally, there is the human implication, the one that sits at the edge of our understanding, the one that makes scientists speak in careful tones. 3I Atlas changes its rotation freely, calmly, predictably, without any known source of energy. It is a reminder that the universe still holds domains where our laws bend, where our certainty trembles, where silence carries weight. As it drifts outward, its spin will continue to rise until its distance overwhelms our instruments. The darkness will swallow its signal, one pulse at a time, until the anomaly fades from our reach. But not from our memory, because somewhere in the quiet between stars, a small shard accelerated without cause, and for a brief moment, it showed us that the universe can still surprise us. Without sound, without warning, without explanation, and in that silence, we are left with a final thought. If 3I Atlas can change its rotation in the dark, what else is waiting in the spaces where our instruments cannot see?